Hello and welcome to the 8th session of our playlist, where we're trying to learn about agentic workflows using LangGraph. So this is kind of the last installment in the human in the loop section for this playlist. And today we are going to talk about a concept called as time travel. So first of all, we'll check out the intuition and we'll try to understand why do we need time travel, what is time travel, and then we will go to the implementation section where we will dive into a notebook where we'll see a simple implementation of this concept. So we learned about approval, we learned about human modified states, but why do we need time travel? What is time travel? Well, it sounds very fancy, but it's a pretty intuitive and a pretty simple concept. Well, the intuition behind it is, for example, a user is having a conversation with a graph, and midway in the graph, he realizes that he wants to change the input. He wants to change something in the input section. He wants to go back and kind of resume the graph's execution, resume the conversation rather, from a prior step, from a step that he has already completed. So he needs to time travel, right? So we can enable this time travel thing in our graph using the concept which you're going to learn today. So I've written here that what if you want to go back to a prior step and change the input to explore a different conversation path, providing flexibility and smoothness in a convo. Well, simply you can imagine this like, for example, we started with an input something like what is the weather in San Francisco, and the graph is executing and we are having a conversation with it, but midway we realize that okay, I shouldn't have asked it about the weather in San Francisco. I should have asked it regarding the weather in a more specific place, in my town specifically. So you can go back to the prior step, the step where you provided the input, and kind of reinitiate and resume the conversation from there without having to start another session in that same conversation. So there's these words, flexibility and smoothness, come into the picture. All right. So today we are going to look at a React agent, our beloved React agent, and enable it with a time travel feature. So it's a simple graph. It's starting from the start. It is taking multiply 3 and 7 as input currently, going to the assistant node, which is the LLM node. Then it goes to the tools condition where it checks if it has a tool calls or not. If it has a tool call, goes to the tools node, utilizes the multiplier tool to give a response back to the assistant node, which in turn provides us the final response to the end. So in this section, it's very simple. We're just providing multiply 3 and 7 as the input. What if somewhere in between, somewhere here, even towards the end, we realize that we shouldn't have asked it multiply 3 and 7. I want to change the input to something else, maybe multiply 5 and 8. So I realized that, all right, might get a little bit of beef for this. So I realized that I need to modify this. So pay attention to this, that I am modifying this state, I am overwriting this state, I am not appending another message on top of this initial message like we did in the last video, like we did when we were talking about that human feedback node, where we were basically adding another message on top of our input message. Here we are talking about going back to this step, overwriting it with a new input, and again kind of resuming the execution from this particular step, this particular node rather. So I went back here, somewhere in the graph I realized that I need to change the input. I went back here, I changed the input to multiply 5 and 8, again everything continued, and I got a response. The product is 40, and I take it, I accept this. So this is the concept behind time travel. This is the kind of understanding that we need to have. We are basically going back in time to a step changing that step, and resuming the execution of the graph to get the desired response out of it. Let's move to the code section now. So first of all, I'm just creating the normal React graph, add, multiply, divide tools, defined them, binded them with our LLM, created a system message. You are an assistant to perform arithmetic operations, the generic one, simple one. Added nodes and stuff, the tools condition, the tools node concept. Did go this one here. Enabled it with the checkpointer feature, and our simple generic React graph got created. You can see it here. Now I'm beginning to execute it in the way we did before. The initial input is just multiply 2 and 3 here. We executed it, configured the thread, used the graph.stream to execute it, and we got this response 6. The result of multiplying 2 and 3 is 6. Cool up till here. But now let's talk about how can we go back and redo this step, redo this particular step, change this step, and resume the execution of the graph from here again. For that, we need to go through a little bit of tussle with some of the methods. So let's see them. Let's see the current state of the graph after the first execution using graph.getState. We know about this method. When we do this, we basically see the current state. So the current state is this. If you scroll over here, it basically is a super state of all these states. So it kind of has a lot of information about our current execution, every single thing. So if I go up till here, or if I just write it something like current state equals this, and then I go over here and I write current state.messages. All right, let me just check what it was again. Yeah, dot values, and then messages. So you can see that it contains all of the messages because it is just a super state. This particular current checkpoint is a super state of all the previous checkpoints. So multiply 2 and 3, tool call, 6, and everything, right? We know about this. But we can use the getStateHistory method that I told you about in the last video as well to get the entire conversation history that happened in that particular thread that we configured. So the graph.getStateHistory is a generator object that we can use in the form of a list by using a list comprehension. So when we do this, the entire state history or the entire conversation history we can get in the form of a list in this state history variable. But there is one kind of a peculiar fact about this getStateHistory method, or a very intuitive fact rather when you get to know it. It is that just a second. Yep. So state history gives us, so currently the state history variable which we have here is just a list of all the messages or all the conversation which we had with our graph up until now. So it is just kind of a collection of all the checkpoints. But an interesting fact about it is the first element of this state history is the current state. So it is the latest or the recent most state. By default, we know that for every single list, usually the first elements are kind of the older ones, right? But in this case, the first element is the current state, and the last element is the start step. This one, the start. And as we know that in the start node, there is no message in this. This is kind of an empty node. This is just to define, this is kind of a logical node that defines that the graph starts from here, right? So it won't be having any information. That's why I provided an empty list over here. So after the start step, there comes the input step where we basically go in and we provide some input that gets fed to the entire graph. So the second last element of the state history list contains the input step. The input over here is multiply 2 and 3. So this is one peculiar fact that we need to keep in mind. So I've commented that over here. Here we can see the arrangement of states in this output. The current state is the first element, and the last element will have the start node. So the second last will have the initial input, and that's what we are willing to change. We are willing to change multiply 2 and 3 to something else. So let's go through a few concepts before we do that. So we can get the current state from the first element, that values messages, and the input state we can get from the penultimate or the second last element of state history. Let's see in input state. So this is the input state that we got from here. So the fact is true indeed. The second last element contains the input state. Cool. Now, every single element in the state history list is basically a checkpoint, because state history is a collection of checkpoints. I had explained it to you over here in this particular diagram. You can see this provides us a list of all checkpoints, graph.getStateHistory. Okay. So every single element is a checkpoint, and every single checkpoint has a config. So we can access that config using .config method, and it provides us the configuration of that particular checkpoint. We will see how we can use it to do different kind of tasks. So this config basically contains the thread ID, it contains a checkpoint ID. So using this information of a prior checkpoint, we can time travel in the graph and replay the graph from a particular checkpoint by passing the checkpoint ID and thread ID to the graph stream method. Alright, so it's basically saying that this checkpoint ID over here, or this configuration of a particular checkpoint, is the key to time travel in a particular graph. But before we go into that, what is this replay, not re-execute? What does this thing mean? Let's go back, let's see. So say that we have a prior checkpoints configuration. Say that we want to go back to the input step, and we have the checkpoint configuration of this thing. Okay. Say that we know that the checkpoint configuration of this has a checkpoint ID of say XYZ. Let me write it over here. So checkpoint or the config is something, okay? Something XYZ. It contains more than one information. We know that, but I'm just writing it over here for understanding. Okay, so it has a configuration, and we want to access this particular checkpoint in order to time travel, right? So we know that this is a generic thing. When we provide none as an input to a graph.stream, it executes from the current state. But when we provide a prior checkpoints configuration as an input, then there are two cases. First, it is a previously executed checkpoint. So in this case, this is a previously executed checkpoint because our graph has already been executed, and we are somewhere around here, towards the end or over here, and we are rethinking our decision of providing this particular input, which we want to change, or we want to do stuff with it. So obviously this is a prior executed checkpoint, a previously executed checkpoint. So in that case, the graph directly gets replayed from that checkpoint. Why am I using the word replay? Because this checkpoint has already been executed, right? So say that this entire graph has been executed and we are at the end. And now I want to go back to this checkpoint and change, if I provide this checkpoint's configuration as an input, and just provide this checkpoint's configuration and not make any changes, and I use graph.stream to execute it, then the graph knows that it has been executed earlier, so it will just get replayed. Everything will get replayed, and there will be no re-execution because the graph has already executed with this particular input. So this checkpoint in this particular form has already been executed. That's why I'm using the word replay. So it will get replayed from that previous checkpoint. Now, what is this forked checkpoint? Now, if we decide to go back to this checkpoint and we decide to change the message or change the state by overwriting it to something else, here we are overwriting it to multiply 5 and 8, then we call it a forked checkpoint. So forked checkpoint is nothing but when we overwrite or change the state of a particular checkpoint, it's called a forked checkpoint. When a checkpoint is forked and we provide that prior checkpoint's configuration, and that checkpoint whose configuration we are providing is forked, then because the graph had not been executed using this particular input, it will get re-executed and not replayed. So that's the difference. So this configuration is very important, and using this configuration we can time travel, replay, not re-execute, or even re-execute a graph from a particular checkpoint. So in this case we are seeing the replay part. How can we replay the graph? So I want to replay the graph from state history -2. It means that I want to replay the graph from input step. And as we know that for every single checkpoint, there is a metadata called next node. So we see that the next node is assistant node. So we are on the right step indeed. So we are replaying this graph. So a replaying does not have a different syntax. It has the same syntax, but in the config section we are providing this particular checkpoints configuration. So my bad, I've just made a small mistake over here, that the input will remain none. How did I not see this? In the config section we are providing the configuration of the checkpoint, and if you want to execute it from the current state, in the config we provide simply the config or the threads configuration. All right, so that's a small change, guy. I just made a mistake. So the concept remains the same. So you can just think about it in that way, that we don't need to change the input. We just need to change the configuration part, because we know that graph.stream has 3 things that we need to provide it: the input, the configuration, and the stream mode, right? So pretty intuitive that you need to provide the checkpoints configuration over here and not in the input section. Cool. So we replayed the graph from this checkpoint, and everything went the same way because we did not change anything. So this got replayed. This is not a re-execution, it is a replay, because this entire thing had been executed earlier as well, as we can see here. Now we want to rerun the graph from this checkpoint with a different input. That's what we are looking forward to, right? We are looking forward to time travel to change the input to explore a different conversation path. So for that we need to do forking, right? We talked about forking, we need to do forking. So we can also rerun the graph from a previous checkpoint, but this time with a different input. This concept is called as forking. And if we fork a checkpoint, it won't be a replay, but it will be a re-execute. Now in the same way, let's define which checkpoint do we want to fork. So fork state equals to, again, the input step. We want to fork this particular step, and we are looking at the message ID of this particular thing. Okay, so in this case right now it's 2 and 3. Okay. And let's say that we are actually trying to recreate the scenario in our code over here. So the product of 2 and 3 is 6. These are the values that are floating around in our code right now. So what we are doing over here is we are looking at the message ID. We know that for every single message we've got a message ID. We have got an M ID. Okay, so it has got an M ID. And we learned about a concept in the last video, that if we provide a new message to the add messages reducer alongside a messages ID that matches the message ID of an existing message, then instead of getting appended, it gets overwritten, right? If you have confusion regarding this, you can check out the last video where I've explained this. By last video, I mean in Agentic Workflow 6, I've explained this. So that's exactly what we do in forking. So in forking, we are updating the state, providing the configuration as the fork states configuration, because that is the state that we want to upgrade, that we want to update. And in the values section, I'm providing a message ID alongside the new message. And this message ID is of the same checkpoint which I am trying to fork, because this is the message that I want to overwrite. So I'll be using the message ID of this particular message. So I know that the fork state is the input state, and I'm using the message ID associated with the fork state. So I'm basically trying to override this to something else. I can go to red, multiply, I guess it's 5 and 8 over here. Cool. 5, 8, but it will have the same message ID. So if the message ID over here was 1, 2, 3, the message ID of this thing will also be 1, 2, 3. So this got overwritten and not appended, because that's how add messages reducer works. Okay. So we update the input state with the new input, use the reducer to overwrite. As I said, the reducer is none other than add messages reducer, providing message ID, refer agentic workflow 6 for this concept. Cool. Now we're re-executing the graph. Now that we have a forked checkpoint over here, this is the forked version. Now because it is a forked checkpoint and the graph has not been executed previously using this particular input, so it will get re-executed and not replayed, and we will get an output over here which will be the product of 5 and 8 is 40. So we executed it again using the fork config. That is, we're executing it from here using the configuration of this particular step, the forked checkpoint, and we got the response as 5 and 8 is 40. So pretty cool. We time traveled back to this step, we changed it, and we re-executed it to get the desired output. This is what time travel is all about, guys. Right. Now, let's again see the current state. Looks as expected. Multiply 5 and 8, every single thing is as per the expectations. So now that we saw this, I've created a small as the demonstration for you guys, so that you can also understand how it works in a different kind of a scenario. So I've created a very simple kind of a code that you can check out in this notebooks. The link of this notebook will be in the video itself, description section. You can check it out and make some changes, play around with it if required. You're always free to do that. You're always free to play around, right? Even while you're working. Okay, cool. So here I have just created another tool, which is a web search tool using the Tavily. You can check out the code. And I have all of these tools in my arsenal right now. In addition to adder, multiplier, divider, we also have the web search tool now. So this is just kind of a demonstration. And I've created a system message. You can check all of this out. Binded everything to the LLM. Created the graph. Cool. I have used the interrupt after. We have learned about interrupt, how interrupt works in the previous sessions. And I'm executing it. Now let's execute it. Cool. Now it's asking me, hi, ask a question. So let me ask, what is the capital of England? I can help you with arithmetic operations. Let me know if you have numbers you'd like to work with. All right, let's see. What's the issue? Maybe, just a second. Maybe I need to run everything again, because it is telling me that I don't have a web search tool, but I have it over here. So let me just rerun it. Shit happens. Right. Let me check. We have the LLM. Cool. Yeah, let's wait. Just a minute. I should also change the thread ID. Let's change it to something else, maybe 56, anything. All right. Cool. Let's re-execute it. So I'm asking it, what is the capital of England? and it is processing, called the tool, and I had an interrupt after, as you can see, interrupt after assistant. So this is the LLM response, which is a tool call to the web search tool, and after that it got interrupted, awaiting my response. Should I continue, yes or no? So I'm saying no, I want to change something. And it's asking me, do you want to change input? I would say yes. Provide new input. I want to look at what is the capital of Finland, rather. This is the thing which I'm looking forward to. Now it's executing with what is the capital of Finland. It initiated the tool call. Again, this is the tool message out of the web search tool. And this is the final response which I got. So here what I did was that I started off with what is the capital of England, but then again I time traveled because I wanted to kind of change my input. I wanted to look at what is the capital of Finland instead. I executed it and I got the response. So this is a very simple demonstration of how time travel works, and you can do a lot of things with it. And you can also look at the different kinds of errors that I come across, so that you can also think about them, how to avoid them, things like that. I usually try not to trim them out, so that, because the errors are very important, failures are as important as success, right? Not to sound too catchy over here. So I think that's it, guys. Thanks for learning, and I'll be trying really hard to chunk out good amount of time to create a working LangGraph application. I mean a good application, because I know that we've been working with pretty basic stuff. We've been learning a lot of concepts up until now, but we've been working with pretty basic kind of graphs up until now. I'll try to create a working kind of a conversation engine using LangGraph in the next video. So stay tuned, and hopefully you learn something. And thanks for watching. Keep learning. Bye bye.